if you're using my VM, you don't have to worry about doing this. There's already a compiled version of this program. But if you are not, for some reason, we do need to compile it. So we want to do GCC, the GNU compiler, and we can put debug symbols in there with -G. And let's see, we need to put a flag in there, fno-stack-protector. What that's going to do is turn off a stack protector, or a canary as it's called. We're not going to cover the canary in this class. If you continue with exploit development, do an exploit development class, for instance, you probably will work with canaries, but we're going to start with the basics here, so we just want to turn it off. And -O for the output, I'll just call mine overflow test. It's just going to overwrite the one that's already there. And the input file is overflow test.c. The main thing we need to do is just fno stack protector. The debugging symbols we don't really need, and if you change the output to something else, it will give it that name. And if you don't put the -O, it will call it a.out. A.out is fine. We don't really care what it's called. It does throw a warning. Basically, it says that main is not an integer. I made it a void. Whatever. Still compiled. That's not the source of our buffer overflow, that's just it complaining about things it doesn't really need to complain about. Alright, so now that it's compiled, we can go ahead and run it. So overflow test from our current directory, and remember it does want user input, and since we know the source code, we know that it wants basically 4 characters, because string ends with a null byte. So someone pointed this out to me in a class a few years ago, so it's just like, oh, it can be 5 characters, and you'll see that it can be, but technically we will have actually overflowed the buffer. I say that with air quotes that you can't see, because if it doesn't actually cause a crash or anything, it doesn't particularly matter, but technically if we give it 5 characters, we have overflowed our variable at least by 1 character, because that null byte at the end will actually make us write to adjacent memory. So let's stick with 4 characters to be precise. So overflow test with 4 uppercase A's, and it prints out executed normally as expected from the source code. But what happens if we say overflow test and then just, be heavy-handed about it? It doesn't particularly matter how many we put in at this point. Just held down the big A for a while. We do not get executed normally. We get something called a segmentation fault, so we have made the program crash. So it clearly has some sort of, if not exploitable vulnerability, then at least, it's not very good at dealing with unexpected input, which is generally a good place to start looking for vulnerabilities that can be exploited. So naturally, as exploit researchers, we would want to know more information about what exactly is going on here. So what we're going to use is a debugger. When we move over to Windows, we'll use a more graphical debugger called Immunity Debugger, but here in Linux we're going to use a command line tool called the GNU Debugger, or GDB. So we use GDB until it's open overflow test. We get, some stuff written out to the screen. Says this is the GNU Debugger. Hooray. Alright, so if you don't know anything about the GNU Debugger, don't worry. You can read manuals about it. I've never found the manuals to be very beginner friendly, but there's a good tutorial series at cybrary2 that I would recommend, or just playing with it. But for this class, we don't really need much GNU Debugger information. Anything we are going to do, I'll show you, and we're certainly not going to cover all the things that it can do. We're just going to look at a basic example here. Debuggers aren't made specifically for exploit research. They are primarily made so developers can debug their programs, see what's going on, but they are widely used by exploit developers to try and build exploits, as we will do. Alright, so let's go ahead and take a look at the source code. Since the source code is in the same folder, we can do that. We can actually list out our source code. That's going to make life a little bit easier for us. Naturally, since C is compiled, we will not always have our source code, so we may have to work a little bit harder. When we move to our Windows examples, we won't have source code, so we'll have to work entirely with what's in memory. But here we do have our source code, so if we do list and say 1, 16, there are 16 lines, so that's going to list out 1 through 16, as we see here. So what we're going to want to do is actually set some breakpoints, which are breakpoints, as the name might imply, is they are going to cause the program to pause or break when we hit them. We don't have to set them on a line like we are here, we're just going to put in line numbers, but you can also have them set on a function or a memory address, lots of different ways to set them. But again, we'll start with something simple here, and I want to set 3 breakpoints. I'm going to start here in main. I want to take a look at the state of memory right before we call function. Remember, function is where the bad stuff is going to happen. We have that string copy function that, since we have the source code, we can probably tell that that is the source of our problems, why we're getting that segmentation fault. So let's go ahead and set a breakpoint here right before the call to function. So if we set our breakpoint on line 14, that will pause execution right before our function is called, so right before that line is executed. So break 14, so we just tell it to break on line 14. Sets breakpoint 1 at the memory address of line 14. And then if we do a break in function, so then we will be in function, and I want to do a breakpoint right before string copy executes. Again, string copy is the source of our trouble, so we're really interested in what happens there. So for reference, we'll basically get a snapshot of memory right before the string copy happens with our break 10. And then right after, we'll just break at line 11, so right before function returns, we'll see what happens during string copy. So we'll see the state of memory after the string copy has occurred. So finally, our third breakpoint will be break at line 11. So 3 breakpoints. Again, break 14, break 10, and break 11. So break in main right before a function is called for reference. Break right before the string copy, again for reference, to see what memory looks like before the vulnerable function. And then finally, right after the vulnerable function at line 11. Alright, so now we've got our breakpoints, and let's go ahead and run this. So to do that, we do say run, and we give it any input that we need. So again, let's start with 4 A's. Again, 4 bytes here, and go ahead and hit enter. That will have it start, so it'll either run the program till it finishes or it hits a breakpoint. We hit our first breakpoint, which is the breakpoint 1 at line 14, so right before the call to function. So now that we're at a breakpoint, we can examine our memory. So there's lots of different ways you can do examine. Like, it has lots of different ways you can format the output and say how much data you want. So we can say help X. So that's one way of getting data. Like most programs, we can say help and it'll give us some help information. So he tells us more details about the examine command. So basically we say X/ the format we want and then the address we want, which we can give it like a register name or a memory address. And so what we're going to do, and this is certainly not the only way to do this, but this is just the way I was taught, I guess, and that's what has been useful for me. So I'm going to examine / so it's X/, and then we tell it the format we want, which I want hexadecimal. We're going to see lots of hexadecimal in exploit development, so you'll have to get used to reading some hexadecimal if you continue in exploit development. And I'm going to tell it I want words, so W, and I'm going to tell it I want, how about 16 words? That will probably be more than we need. So we'll see how many we need to get to the bottom of main stack frame, but I'm just going to tell it I want to examine 16 hexadecimal words from $ESP. So that, remember, ESP is the top or lowest memory address of our current stack frame. We're currently in main, so we paused right before we called function. So this should show us main stack frame and probably a little more depending on how big main is. We did ask it for 16 words. That's probably more than we need. Alright, so how we can read this is these are the memory addresses over here, and here's the data in them. So this is in hexadecimal, so there's going to be base 16, so 4 bytes here, 8, 12, 16, and then we wrap back around, so we go up to 9, and then A, B, C, D, E, F, and then loop back around to 0. Alright, so this would be the memory location of ESP, so the top of main, and this would be whatever is in there. So to get a reference of where main ends, we would need to examine, we just need one hexadecimal word here from EBP, which again is the bottom or highest memory address. So notice that we do go to higher memory addresses as we go down the stack, so C, D, E, F, so going higher there. So it says EBP is at C8, so indeed 16 hexadecimal words is way more than we need. It looks like this is main stack frame, so not much to it at all. In fact, only 12 bytes. Then again, main doesn't do very much, so that's not entirely surprising. Alright, so that again is just a reference. Nothing particularly interesting happens in main, at least from an exploit development perspective. So to move on and let the program continue, we say continue, so that will again either go to the end of the program or the next breakpoint. So we hit breakpoint 2. We're now inside a function right before the string copy. So we can hit the up arrow to get our old instructions back. So if I just go up to my examine 16 hexadecimal words from ESP, now that we're in function, ESP will now be pointing at the top of function stack frame, which should have been put on top of main stack frame, so we should have lower memory addresses, because again, stack moves up towards lower memory addresses, so we should see B0, A0 over here. That's indeed exactly what we see, so here's A0 at the end here. And we can again get EBP, which again should be pointing at now the bottom of function stack frame. So it says it's at B8. So this is part of function stack frame as well as this here. So a little bit bigger stack frame here. 5 of those bytes are going to be for buffer. We don't know which 5 those are yet, but we will see that presumably after the string copy. We should see our A's show up, and we should be able to tell when we hit our next breakpoint. So remember, if we look up here, so starting at our C0 is where main is. So this is main, it's stack frame, and this is function. So what's this? So if we remember our picture, when I showed you the slides in one of the previous videos, we have main stack frame. On top of main stack frame, we should have the return address, so the memory address of the next instruction to be executed when function returns and we go back to main, and then we should have function stack frame. So this should probably be, if in fact my theory is correct, this should be our saved return address. So 08048443 should be a memory address in main that should be our next instruction to be executed. So we can disassemble a function. So if I say disassemble and then main, tell it to disassemble main. Here's some assembly. You may not be too familiar with assembly, and I particularly, this is in AT&T format, and I prefer Intel format, so even though I do know a fair amount of assembly, it's rather hard for me to read these because the formatting is a bit different than what I'm used to. We can change that if we want to. We could do set disassembly dash flavor. You don't need to do this if you don't want to. I can't spell disassembly apparently. No, I can't. Alright, so set one S here, simply flavor. My spelling is getting worse by the minute. Intel. I misspelled it again. There's an E there. There, finally, no error. So, set disassembly-flavor to Intel. Again, you don't have to do that. I just prefer Intel format, so this format is much easier for me to read. But luckily, it doesn't particularly matter if we know assembly, because we're interested in what is the call to function, even if we can't read assembly call and then function. That even if we can't read assembly, that pretty much jumps out of it at us that is indeed the call to function. So our next instruction to be executed is probably this one. I mean, that would make logical sense. So 08048443, which I've run off the page because I can't spell disassembly. So if I go back and examine again from ESP, so we have 08048443 is our saved return address. So that should be the memory address of the next instruction to be executed. Sure enough, that's exactly what the next assembly instruction in main after the call to function is. So it looks like everything is exactly like my picture said it would be. How interesting. Alright, so let's go ahead and continue again. So let's let that string copy execute so we can see what happens in memory. So we have this as a reference. So this again is function stack frame now. Let's see what changes when we let string copy run. So if we continue, we hit our third breakpoint right before function exits at line 11, so after the string copy. Again, let's examine our memory. So, a quick reference here. It looks like a few things have changed, but in particular, 41 is hexadecimal for an uppercase A. You can look at a man page for ASCII, and it will actually show you all of this, or you could go to like ASCIItable.com if you need to reference what is what. I mean, certainly I can't expect anyone, since I don't even, to know all of the ASCII table, but as you spend more time with it, like 41 you'll probably remember, because for whatever reason, typically people just start overflowing buffers with bunches of large A's. So you see lots of 41s in memory, but if you need to check what it correlates to, you can always look at an ASCII table. Again, there's man ASCII, or I like ASCIItable.com if you like something a little bit more graphical. So we have 41 here as the first character here, and we have 41, 41, 41, and then a null, which again terminates a string. So it looks like that's where our 4 A's showed up, so this should be where that buffer variable is, and it did indeed fit nicely inside of our stack frame. So again, the return address is all the way over here, so you can kind of start to see an idea of what we're going to try and do, since we want to get control of that saved return address. If we, instead of putting 4 A's in, we just kept putting A's in, and that string copy would allow us to overwrite adjacent memory, and would eventually could overwrite as much as we liked, really. But for now, it did all fit nicely. Our only question is, why is this one off by itself, and why is it like turned around? It's like the null that's the end seems to be byte number 2, if this is byte 1 and then 2. So it looks like things are a bit backwards, which when I was first starting exploit development, this really baffled me and made me waste a lot of time. So we will see exactly what's going on here, and if I teach you one thing about exploit development, you will never make the same mistakes I did. So we'll see that in our next video. But for now, let's just go ahead and continue and let the program finish. It does print out executed normally, and the program exits. So since we only used 4 characters as our input here, everything works fine. And again, naturally, the next thing we're going to do is try and overflow it.